Good. So let's continue or talk about network design and in particular buy-at-bulk network design. That we talk about Steiner tree, Steiner forest as special cases, and we mentioned that in general, in the buy-at-bulk network design for each edge, there is Fe of P, that according how much bandwidth or how much flow is going there, that would be the cost of that. And that we discussed that is up to a factor 1 plus epsilon. This is equivalent of cost distance problem, that on each edge you have installation cost C, and the length function L is the rent things that you are giving, or per use routing cost. Installation cost, as soon as you are using, you need to pay. And then we have a demand per SITI, and we want to have send traffic demand DI between them. The total cost is the objective function that we try to minimize. This would be essentially equivalent of this for those edges that we are buying the essentially using them, we need to pay the installation cost. For all others, we just consider the shortest path on this both edges, and then you need to send the demand DI along that path. And that would be one path, because, I mean, essentially if there's the shortest path, it does not make sense to send it to different paths. So this routing through one path comes as a even without constraint. You try to minimize the total cost. And we discuss about some special cases, uniform multi-commodity. That's the thing that the previous time we talked about, Averbach and other. That was the idea that there was like an approximation, and it was using two ideas. One essentially is this kind of Bartal or FRT embedding, and also the fact that it is uniform, all edges are the same, and the fact that as long as you are sending more flow there, then we had this kind of sub-additivity or economy of scale that only can save. So we talk about it. It was not a trivial one, especially at that time, but that was not a hard one as well. As I mentioned, there was nothing for the multi-commodity non-uniform buy-at-bulk before. Single source buy-at-bulk also it exists essentially, especially these 2% of Meyersons are very good one to look at it. And these are some randomized algorithm, very nice algorithm that you can actually get Laguerre approximations there. But here we just use them essentially. But this was the thing, that how can you get the multi-commodity flow? And this here we show actually how embedding into a spanning trees was very helpful essentially versus just FRT. So this is the theorem that say for each number of SITI pairs, and again, the SITI, the demand is DI, we obtain a practical polynomial time algorithm with approximation log H to the 4. So it is like somehow independent of log n, but here for simplicity, we are assuming that all the demands are 1, and we are giving O tilde log n. But this can be improved essentially further. And again, so this is the thing, these are the demands are given to us. SITI, this is the demand of DI is given to us. And each edge here, it has the CE and LE. CE means the cost of this edge. If you want to use it, you need to buy this edge. This is like more like a Steiner tree or a Steiner forest. And LE is the one that per usage, how much flow you are sending, you need to pay that. This is more like a shortest path, because shortest path actually pays per usage. So in some sense, we have a combination of rent or buy. That's the thing, that this kind of buy-at-bulk is also very related to rent or buy set of problems. Good. So let's talk about the algorithm. And the algorithm, I mean, it's nice. It was actually very innovative when it was essentially discovered, or rediscovered. So, and this is the algorithm that actually can be used for several other problems, and the approaches of this has been used for several other problems. Even some problems like dial-a-ride or others which are not completely relevant to this, the technique has been used. We will talk about them. So what does the algorithm do? The algorithm iteratively finds a partial solution, connecting some of the residual pairs. So these are some of these, essentially, these are SITIs. It connects, find a partial solution, means that it's connecting some of these guys, and then, of course, route the demands, and then find new pairs and just do that as well until everyone gets connected. So as I mentioned, when you route these guys, then you will remove them from further consideration. We do more, and then we are done, essentially, until everyone gets connected. So that's the algorithm. Now, here we need to define the density of a partial solution. Density of a partial solution, that's the one which is important. This is, in that sense, this part is very similar to set cover. So this kind of greedy and essentially using density for a local search has been used a lot, but this is, I mean, it was, how can we define it and how can we use it was interesting here. But in general, this is the idea that, like this idea comes from set cover. You will find the density of a partial solution. So it means that the cost of the partial solution over the number of new pairs routed, that you have defined such a thing for set cover. The so there we had the same thing, that the cost of a partial solution was the newly covered cost of the set over the number of newly covered elements. And here the density, in some sense, is the average cost per new pair. So the algorithm tries to find a low density partial solution at each iteration, connects them, and then go ahead, essentially. So in some sense, this low density is the one that you don't find the rest, the whole thing, but you are finding a low density ones. You will connect them. It has a local cost, essentially, is good, and then you will continue. So what we can show, we will show that the density of each partial solution in our algorithm is at most O tilde log n to the 3 times opt over h. Where opt, of course, is the cost of the optimum solution, and the h prime is the number of unrouted pairs. So that's so we want to get log n to the 4, essentially, O tilde log n to the 4. And you will see exactly all where are these logs that are coming from, whether we can improve some of them or not. So here, we said that we can create a partial solution. We show that there's a partial solution whose density is at most log n to the 3n times opt over h. Then from this is very similar to set cover analysis that we have already done. We can show that then the cost of, or total cost, would be log n to the 4. Why? Because you can see that, like, when you are adding h number instead of essentially 1 over h, so these are the maximum number of pairs would be n choose 2, which would be order n to the 2. So that's the reason that now, given this, that it is over h, you can say that here this would be always essentially more like essentially more cost comparing to this h things, because when you put it h essentially, so this part is very similar to set cover. We discussed already there, so I don't want to go through this one. But you can essentially, whenever you have this kind of partial solution that it's talking about the remaining number of pairs, then you can write this type of thing. And here, the important thing is 1 over n to the 2, because the number of pairs can be actually n to the 2. And so that's the thing that we get it. And this would be harmonic number. It would be ln of n to the 2, which is essentially ln of n, or 2 times ln of, or order of n, which is 1 log more that we. So in the rest of this talk, we just talk about how can we find a partial solution, which is at most this. And that's the part that becomes more interesting. So what is the structure of a near optimal solution? So here we try to compute a low density partial solution. This is the one that is, we call it a junction tree. We try to find this kind of low density partial solution, which are in the form of a junction tree. Now, what is a junction tree? So a junction tree is a given set P of pairs and a tree T rooted at R. If you have this property, first, it should contain all pairs of P. And then for every pair SITI belong to P, the path connecting them should go through R. So here, this is a junction tree. We have this root R. It has these pairs S1, T1, S2, T2, and S3, T3. It contains all of them. And the path between these pairs, all of them goes through the junction, which is R. Why are we doing that? Because we try to make this one more similar to the single source case. If we know that these guys are going all through R, then we can make sure this will be a single source in the sense that all these pairs, I mean, both endpoints of this pair should be just connected to the root, and then we are in a good shape. And there, of course, we can use the log-n approximation for, this is single source Buy-at-Bulk, which is SSPB. So here we have two ingredients in our proof. The first one, there is always a partial solution that is a junction tree with density order O tilde log n times opt over H bar. So we show that there exists such a partial solution, and densities is log n times opt over H bar. However, to find such a things, we need to pay another log n to the 2 to find such kind of low density junction. So there exists one, but if you want to actually find it, you need to pay log n to the 2 more. And then we are getting the thing that we wanted. Combining this one is the one that we had it. So then we can find a partial solution, which is log n to the 3, and then we have an approximation, which is order log n to the 4 for that. Good. So that's the whole things. Now let's go and essentially prove theorem 1 and theorem 2, and then both of them are actually very interesting. I mean, that has been simplified, that this is the way that is presented. I mean, hopefully you should be able to get the whole proof. And it was, again, this problem was open for a while, essentially, but you can find actually a nice solution. So first, we said that we can provide a junction tree, which is a partial solution with density order log n times opt over H. Consider the optimum solution opt. E star be the set of edges that opt installs or pays essentially the installation cost C. So opt C be the installation cost, and opt L be the total length per use case or routing cost or renting cost. Of course, opt is equal to opt C plus opt L. That is by definition. And note that, again, for different edges, we may have different C and L. That is important, which was not the case for the uniform. For the uniform, everything was the same, and that was very useful. This was one of the most important things, actually, the observation that I have made, and that was very useful. I mean, of course, not this observation, the next one. Opt may have cycles. This is the problem that makes this problem much harder than the previous, like Steiner Forest or others. Because there you could say that the solution is actually a forest. And then note that we try to actually find some kind of junction trees. And these are the trees. But here we have a cycle. What can we do? So this is the main part that actually you can use this result of Elkin, Emek, Spillman, and Tang, or Abraham Bartal Neyman that we talked before. This is for embedding into spanning trees. They say that you can probabilistically embed onto spanning trees by losing a factor order or tilde log n. And the best one currently is still something like log n, I think log n or something like this. But like it is O tilde essentially, it is log n plus some log thing. I mean, in the FRT note that we had exactly log n, but here in this guys we have some this kind of log things essentially extra. I think there's another one, Abraham Barthal in 2012, that is slightly improving this log part. If we use this one, then we can assume that E star is a forest. And we only pay order log n more on the length. Why? Because this is important. So we apply this theorem existentially. So we apply the theorem existentially on opt. And this is the most important. So this one, we apply this one. Yeah. One question, because the theorem of the upper bound on average length. Yes. So now we don't make it actually in this way, the perpendicular have larger but on average. Yes. So we only consider we need to consider only one of these three. So we can just essentially use linearity of expectation, and just say that in one of the trees we know that the total cost of the total cost it would be log n more for the renting, and so the cost of buying essentially. So you can still use this kind of averaging. And so you want to get essentially from these trees, so you consider opt, so you will apply essentially this theorem on opt, and you are getting a set of trees, and you will say that on one, I mean, this is the trees essentially, and you will say that on one of these trees, the installation cost, I mean, would be essentially less always, and the total length would be at most like. Yeah, but I mean, if you look at the distribution of the trees, you look at the fact that in the graph, the very short x16, then in every tree from the distribution, it might be that the distance between this two vertices is larger than log, because it doesn't matter, because the average still is very large. So basically, it doesn't classically matter. No, you can actually, I mean, for each pair, we have the thing that it is log n. Okay, yeah. So for each pair, we have the log n essentially. That's the thing. I mean, there are two versions of that, but this is the stronger version that we have. Yeah. For each pair, we have it, and then we can essentially pair by pair think that. So we are. This was very crucial, essentially, this theorem for this one. Otherwise, I mean, that it was. You see, that was the 2005, the first version of. This is the one that we can assume that essentially there is one tree that, I mean, here we are losing log n on the length. The cost is still would be just the same or less actually. We are losing log n one more essentially there for the cost as well. But here we get one tree essentially. From this we get a tree. Now, from T essentially, we obtain now we have a one tree essentially, but the issue is that this tree is not a junction. So it might be have Si to Ti, like S1 to T1 is coming here. I don't know. Maybe there is S2 to T2 is coming here. And this is not a junction tree. Junction tree, everyone should go through the route. So here, like how can we obtain from one of these trees this kind of essentially junction? From this tree we obtain, actually we show that you can get these trees T1, T2 to Ta, such that each edge of E is included in at most order log n of these subtrees. And for every pair, there is exactly one index I, such that both vertices are in Ti and the path in Ti goes through the root of Ti. So essentially, so the first one is that note that we paid log n more for the rent cost or this. So we paid log n more for the rent cost, or like length cost, or I don't know, routing cost. Here, I say that each, I can just essentially consider this tree. Maybe some edges will be copied into some trees. But then for each of them, but it would be copied at most log n times. And then each pair that I'm considering it belongs to one of these trees and it goes through the root of that tree.
What is there about A matter?
What was that?
The number of these trees.
The number of the trees, I mean, you can get actually, I think, polynomial time. You can get a polynomial number of them.
Also, it doesn't matter if it's like
I'm not so sure that even actually matters.
Okay.
Because this is everything that we are talking about is our existential. No. Here, these trees that we are obtaining actually is, would be a order n or something like this. But the number of trees that you get, probabilistic trees, it can be exponential. But
no, I mean, well, I mean,
Chris
property, that's what I expect that every edge is included in the most log term.
Yes. So I think from this one, you can. So we don't. I think maybe it is ordered even log n, polylog or something like this, but at most n. So we will see the procedure. Okay. Now, if we get this one, we know that the total cost of this junction trees at most would be log n order O tilde log n opt L because of this essentially spanning trees, probabilistic embedding into a spanning trees. Into spanning trees. And then we have log n more because of this log n. So the total cost of all these trees would be order log n O tilde log n times out. O tilde log n times out.
So one question, so the cost of the tree, so let's say T1, it has some edges that are in T, but it can also have edges that are not.
And on these they will be subtrees. You will consider.
They're subtrees of T.
These are subtrees of T.
But then,
let's see the procedure. Then we will. I think that would be more clear. How do we create this? So yes. So we get essentially this the total cost of this junction trees at most this. So it means that at least one of these junction trees has the density that we want essentially. So let me adjust. So here, as I mentioned, so here the cost of the total cost would be log n times opt because of this. And then we know that at least one of these junction trees, because we are partitioning essentially these pairs into this, one of them should have this density that we want. And then we are done. So this is the part that it shows that there is a one that has a good density.
Can you explain how you got the last part?
So you just divide it essentially. You will consider the total cost. So generally, this is very similar to, again, to set cover. If you know the total cost of this one for all pairs are this, it means that one of them should be below the average essentially. So some kind of Markov essentially.
But where do you get the H prime?
H prime is just essentially the remaining pairs. So if we consider this one, anytime that we are, so what is H prime? H prime is the remaining pairs, correct? Anytime we consider the opt, the original opt is also solution for H prime. So H prime is always essentially the remaining pairs. That's the thing that we are talking about. And this is some kind of simple Markov essentials. Now, how can we do that? This decomposition into trees. So we are using this. This concept is essentially, we will talk more about it when we talk about planar graph, etc. It is called centroid here, but it is called like separators essentially. Separators in trees or in planar graphs. What is a centroid? So each tree always has a centroid R1, such that if you remove it, the largest remaining component has size at most 2/3 of the number of vertices. And actually, the finding this algorithm, the centroid is interesting. You can consider essentially from how can we find it. I mean, of course, you can try all possibilities, but this to existence is essentially comes from the algorithm that you can start from one node of the tree. Yeah, you will start from one node of the tree. If you remove it, there is one of them which is greater than 2/3. Otherwise, you found it. If it is the case, then you will just go there toward that direction. So you essentially can have a tree like this. So just remove this vertex, arbitrary vertex. If it is everything is at most 2/3, you are done. Otherwise, there is one vertex that is more than 2/3. Go through this. And then, because essentially, because this one is more than 2/3, it means that the rest of this is less than 2/3. You can show that this procedure, it will end up at the centroid. You cannot loop, you cannot come back. Because each time essentially, so if you want to, like, you can say that you cannot do the loop back because if you want to loop back actually at that time you found the centroid essentially. So this kind of, it gives actually a nice direction for the trees that you can go there and then there. And when you are ending at that time, because we always know that the rest of the tree would be at most 1/3. And so this is the idea. So anyhow, so you can just think about it. This is very simple, that's why we are not doing a loop back. So there is always this centroid for trees. For planar graph, etc., this is quite non-trivial. We will talk about it, but for trees, it's very easy. So what do we do? First, we are adding a tree rooted at R1 to the collection, and the pairs whose path goes to R1. Good. This is the tree. So we know that there is essentially so there is a centroid here. We consider this centroid and all pairs that the path is going through this, we will assign it to this tree. Then we will remove it from the further consideration. Now, why it is important? So what is the main point? The main point is that when we remove this R, everything has size at most 2/3. 2/3 is not that, just the fact that it goes down by a constant factor is the most important. So everything is at most 2/3. It means that the depth, now you will repeat this one for each of these trees. For each of these subtrees essentially. Find the centroid there and do this. Because the depth of this tree, the depth of this recursion would be log n, each edge will appear in at most log n of this tree. And the fact that the centroid was important because the size of these trees goes by a factor 2/3 down each time. So this is so essentially from this tree, for example, you get one tree R1 here, rooted here, and another one R2 rooted here. And this will be partitioned, the set of demands, into the set of these things. And when you partition this demands essentially into, when you partition this demands into the things that you want, then you can use that density argument, because then you can say that this is a partition, this total cost would be, and here we are paying log n more essentially because each edge may appear into log n of these trees. So the additional cost, we are paying installation cost log n here, log n for this kind of embedding into probabilistic embedding trees, but then because separate part in total would be log n, and we get the result that we want. So each pair is exactly one tree, each edge is in the log n subtrees, and the depth of the recursion, because the depth of the recursion is at most. So we are done with the first theorem. What was the first theorem? The first theorem was this one. There is always a partial solution that is a junction tree with density. But so far, everything that we have done it, essentially, this is exactly the thing that we are doing a lot in approximation algorithms. What do we do? So in approximation algorithm, we are doing a lot. Everything that we have done so far, it was just with the opt, some imaginary opt that we don't have access to that. We are always doing this in approximation algorithm. We try to massage opt such that we get some kind of approximate opt that now we can hopefully find it. But here in this case, even to find this approximate cost, we need to pay another log n to the 2 such that we can find. But it is essentially, so far we were just doing everything existentially. There exists such a things that a partial solution that has these things. How can we find? That's actually, it is also non-trivial. Or original solution was for this was non-trivial, like quite complicated. But then later we could actually use a linear programming as I described. Now, I want to say that there is the order log n approximation for finding the lowest density junction tree. Good. And what is a junction tree? For now, I mean, just forget about SITI pairs. So we have SITI. But say that, I mean, forget about it. I want to find essentially this R and this SI and TI, which are all connected to R. Good. All of them should be connected to R. Of course, I don't know who are these demands. That I don't know. And I know that these are just partial solution, not the whole thing. But I want to talk about it. So here, in some sense, it will become very similar to single source because everyone should connect it to the root. And of course, this is the Buy-at-Bulk network design. So it is a single source version. But here, we want to find a low density solution. In single source, we want to connect everything. And then we could pay log n. But here, we don't want to connect everything. We just want to find the low density one because that's a theorem. So we want to connect a subset of these pairs to the root R with the lowest density. And again, here the density is the cost of the solution over the number of pairs in the solution. So that's the thing. This is another technique actually that can be used for other things as well. We try to formulate this one first as an integer program, and then as a linear program, try to round it and say, how does it work? And this is actually again, this solution, the original one was much more complicated. It was a combinatorial thing. This was much simpler things. Okay, so let's write an LP for the problem. For now, we are just talking about the low density single source. So we want to find, so what's the meaning of that here? You have a given essential, there is no pairs anymore. These are some essentially demands that I have it. Each of these demands with some like demand di, say, they need to be connected to the root and say, forget about that we have some pairs. We want to just connect some of these demands to the root with low density or the lowest density. Okay, so this is the LP that we can write it for that. No, no, the pairs actually is quite non-trivial. That's the one that we have done it here. I will talk about the pairs, but not yet. I will handle the pair, but so far we don't have a pair. So we want to connect these guys. So how can we do that? This is the LP that we are writing. So I'm using a flow LP essentially. FP means essentially that this flow is going through this edge. And again, you can show that here that would be through one path. So let T be the set of terminals to be connected to R. So these are the terminal sets. Yi is 1 if we connect a terminal I to the root. So yi, this is an integer program. Xe is 1 if the edge is a North solution. Let Pi be the set of paths from a terminal I to R. Note that we are solving this one on the graph. Everything about the trees, everything that we discussed so far is for opt. But we need to solve this problem on the graph. We don't know what are that trees. Everything that is junction tree, etc., that was only about opt. FP is the flow on path P. FP, this is the general thing. So we are just essentially writing the flow LP. That flow LP essentially sends some flow FP along any path P. And this P essentially is belonging to the P of, for example, I. What is PI? PI, the P capital I essentially, or P cal I, is a set of paths that connects terminal I to the root. And again, this is everything is about in the graph. In the graph is we don't know it's essentially we know that is the junction tree is 3. But here we are just writing essentially for the path because single source actually works for the graph. So what does this LP says? It says that, okay, these are the variables that we have, XP, FP, and YP. And again, the size of this is actually large. FP is the flow LP, essentially. For each path, so for each edge E, for each P belongs to these paths that connects I essentially. And then YI is the essentially, it says that whether this guy is, so this is in the low density. We want to connect a subset of them. For those subsets, yi equal to 1 means that the one that we want to connect. So what does this one say? It says that this is the thing. They say that if this guy is 1, this is the integer form. If yi is 1, it's better that the flow that we are sending through different paths should be the sum of them should be greater. Good. So that says that the sum of the FP over different paths should be at least 1. What does this one say? Say that if edge E is in our solution, if we buy it, you can use those edges that you buy. So sum of the flow, so for any path P and any edge E that belongs to that, the sum of this FP should be at most XE. Like to the amounts that you buy an edge, you can use it. And again, in the integer case, is that is XE 0 or 1 or 0? If 0, it means that you should not send any flow up there. And if it is 1, then you can send the flow 1. And you don't send the flow more than 1. Note that again, the main flow that we are sending here is that demands are 1. We can generalize it because the demands are 1. And it means that the flow is 1. Now, what is the objective function? The objective function is essentially the objective Buy-at-Bulk thing. It said that sum of the CXE, these are the edges XE that we buy, we need to pay the installation cost. Now, what about for the routing cost? It said that for each FP, if you are using the LP and the LP is the length of it, FP times LP, you need to pay that. And this is for all terminals. So this is the objective function that we had. Essentially, this is the Buy-at-Bulk objective function, the regular objective. Then this is the density. That makes it density divided by sum of the yi. So this is divided by sum of the yi essentially. Good. But, okay, so this is, for now, is the IP. Because, I mean, everything is integer. So we need to try to essentially relax it. And even the objective function is not linear because this is divided by something.
One question though. So if you find a solution to this, why is it going to be a tree? Right?
I mean, I don't care to be a tree, essentially. As long as this is less than the junction. I know that in junction tree, it would be a tree. But here, it might be better than the tree. That is fine. I will just use that.
It doesn't have to be a tree. It's just the...
No, this one does not need to be a tree. But you can actually show that this is, even for single source, it can be a tree. But there is no need to be a tree. As long as it's a partial solution that connects a set of things, and this is less than this junction tree one that we had it, you can proceed the solution.
You don't need the partial solution, you just need the junction tree.
Yeah, exactly. Such that I can write this. Exactly. This is actually it's a non-trivial, and this is like, we spent quite a bit to check all of this. It is because that was you see that every part it may break down as such. Good. So here we need to do that, but still we are not done. So we didn't handle the pair case, and we have this kind of objective function which is not linear as well. Now let's try to resolve them. Okay. First, here we had this sum of the yi's. This is divided by sum of the yi's. This is a common trick. Whenever you have this one, you can scale everything and just say, let's put the sum of the yi's equal to 1. So I say that subject to sum of the yi's is equal to 1. I will scale everything essentially. Another thing that we didn't handle, we didn't mention that this was very important. That you see, if this is the like S1, if this S1 is connected to the root and this T1 is connected to the root, but this is the S2. And this is the T1 and T2. So if S1 and S2 are connected to the root, but T1 and T2 are not connected to root, there is no benefit for me. It is not good for my single source case. Because I needed to get essentially both pairs should be connected to the root in junction trees. How can I resolve it? This is actually a beautiful constraint that you can put. You can say that y of Sj should be equal to y of Tj. To the amount that you are essentially connecting a source to the root, the same amount you should connect the sink to the root. So this was actually very lifesaver. This is one very interesting thing that you could actually use it for. This like a Steiner files. So you want to make sure that, like you see here, we were just so far talking about single source. In the single source, just the terminal were supposed to connect it. But here, I want to make sure that my original problem, Buy-at-Bulk, I have been given the pairs. And I want to say that if SI is connected to the root, TI is also connected to the root. Correct? How can I force this LP to have it? I will add this constraints. I say for each pair, if you connect, so what was YSJ? YSJ was whether it is connected terminal R to the. It says that if you connect SJ to the same amount you need to connect YJ.
But Y is binary, right?
Okay, I'm relaxing it now. say that, I mean, this is connect. I mean, this is, yes, yes, you can think about binary, but I will relax it.
So what do you mean by T1 and T2 are not connected?
No, it might be the case that, I mean, the optimum solution tries to just connect S1 and T1 to R, but does not connect T1 and T2. But really, the solutions that are important for us is the one that if SI is connected to that, also TI should be connected. That's the thing essentially that we condition that we will put it to forces. This is the one that we are putting for the scaling. Then this is the LP that we are essentially that we will put it. For all other guys, I'm just relaxing it from an IP to LP. I say that everything is between 0 and 1. And actually, you don't need to really put 0 and 1. You don't need to, lots of the time, put it less than or equal to 1. Because, I mean, in some sense, I mean, already you don't put anything greater than 1. It would be useless to put anything greater. Okay, so now this is the LP that I write it. I will solve this LP. So I will solve the LP. Then I will. So how do I do that? This part is very similar to the one that we had. This is a typical trick. This log n classes, but also this is the same thing that we have, for example, used for the unique coverage. So this is similar to approach for unique coverage. So we will partition the terminals T into log n classes. 1 to 1/2, 1/2 to 1/4, and again, everything would be at most 1. 1/4 to 1/8, and so on, with almost equal y variables. You can say that at a certain point, if the y is less than that, it is not relevant. So these are like the actual one, the number of these classes, log n classes. So I will just divide this according to the yi's. I will divide it into these things. Note that because of now, this is also this condition that I put it, these are equal. Because of scaling, I will just, each of these yi's essentially falls into one of these. Now, I will find essentially a class S of terminals among these log n classes with maximum sum of y variables. Good. So these log n classes that I have, I will find among these log n classes one class that has the maximum sum of the y variable. This is the same thing that we have done it, for example, for unique coverage. Now, I will just focus on that class. Here, I will lose a factor log n because I will ignore all other guys, essentially. Just focus on this class. Now that I have this class, now I will scale every y equal to 1. So I here essentially is the one that so I will do that. I will just focus on this class y on. Then it was some small thing, but all of them are equal. Because all of them are equal, I can just make all of them 1. And then I'm using this log n approximation of this Meyerson and Chakuri et al. They show that the integrality gap of the LP for Buy-at-Bulk network design is indeed log n. What's the meaning of that? It means that I can round this solution to get an actual solution for the single source Buy-at-Bulk if I pay only log n. So I now the things that I have it. What do I get here? So to find it, I'm losing 2 places. One here, log n here, because I'm only focusing on one class, and then another log n because of rounding SSB. So it would be log n to the 2. I think it is mentioned here. So I will get the log n to the 2 to find it. So again, that was the whole general idea for this algorithm. We are considering the whole solution. We will consider only a partial solution. We are massaging up from this partial solution to get a junction trees. And in junction trees, we are losing a log n factor. Then, and also from partial solutions to actual solution, we are losing another log n factor. Now, to find this junction tree, I need to use essentially this LP. I'm using one log n for this class Y because I'm focusing on one Y class and divide it into log n classes. And then I'm paying log n more essentially for integrality gap of Buy-at-Bulk, single source Buy-at-Bulk, and then it is essentially would be log n to the 2 times log n to the 2 before would be log n to the 4. Another interesting thing that that was interesting in this that we are using LP. So this algorithm works. So this works even if DIs are exponential. So this is the beautiful thing about this one algorithm. So even if this demands DI between the pairs are exponential, note that still they can be represented as this polynomial number of bits. But the size of them might be exponential. Still, we can use this LP essentially and this one to get it polynomial-time solution. And this was another open problem, actually. So this not always happen. So generally, when we consider this problem, we consider that these demands are just polynomial, essentially, the demand size. But here, even if it's exponential demands, you can actually get it this log n to the 4. However, this is a paper by Corsars and Notov that they show that if the demands are polynomial, you can get log n to the 3. This can be also, we have generalized this one. Instead of this, you can also, here we are assuming that all this demands, etc., goes through the edges. And the edges have cost. So we have CELE. But you may consider also the vertices. The vertices have cost, essentially CELE. This is called the node-weighted case. Generally, node-weighted case is harder than edge-weighted case. Why? Because whenever you have some essentially edge like this, you can always put on this, you can subdivide it and you will put a node essentially. So instead of CELE here, you can put it CELE on this node. And maybe this other node, you can just put it infinity or like a cost 0 or something like that. So always the node weighted is more general than almost all problems. Node weighted is more general than edge weighted. And you can also generalize this one for node weighted essentially. You can generalize this one if you want to have 2 disjoint paths between this. Instead of 1 disjoint path, you want to. So this is essentially this called like it is for the reliability. You want to have the reliable network design. It is called. You want to have not 1 path. You want to have 2 paths essentially. If one breaks, the other one breaks. If this graph is directed, then you get a square root of an approximation. This can be also done essentially for some kind of stochastic linear tree with non-uniform things that essentially you can read about this kind of stochastic optimization that was there and that you can also expand. The same technique here that we have used, especially this part about this optimum that you can divide it into trees, etc., that can be used also for Deiler-Wright problem. What is a Deiler-Wright problem? That's important. That's an Uber problem in some sense. The Deiler-Wright problem is that, you can essentially, you have a car or a van, and it has a limited capacity. What is the goal? So the goal is that, these are some of these guys are given, like the people. I want to go from SI to TI. So these are the sum of the riders. I want to go from SI to TI in this graph. Then can you tell me what should be the route of this van that picks up these guys and then put them at the destination? And with the minimum total length, essentially give the right to all of them and the people should be moved from SI to TI. This is called the Euler-Wright problem. That was actually much before Uber existed initially. This also can be used there, and I think I think it was SQL root of an approximation. There was some Fox paper before that. Actually, this one could improve that. This is another one that is also interesting. Is this one, the log n to the 3 for uniform Buy-at-Bulk? This is oblivious network design. What is oblivious? So these are some of the concepts that I want to mention essentially. So here I mentioned polynomial versus exponential is sometimes important, can be non-trivial. You can think about in your problem something like this. Node weighted versus edge weighted. That's I think another one. When you get it for edge weighted, you may want to generalize for node weighted. This is the two disjoint paths or R disjoint paths. So when you find one path between these guys, you may want to find several disjoint paths because that is some problem. You may consider directed graphs. That's another. This is another one. This is a stochastic Steiner tree. The stochastic one essentially is that this is called Monday, Tuesday cost. What is the idea? The idea is that at Monday, you have some cost for the edges. You can buy some of these edges on Monday. At Tuesday, but the demands are coming on Tuesday. So the Monday, you have the cost, cheaper cost. Tuesday, the demands are coming, but at that time, the cost of each edge, if you want to buy, there's the inflation type. You need to pay lambda greater than 1. This is called inflation. So this is the thing that now, like a Steiner tree problem. You want to, there are some costs for the edges you can buy Monday. Then tomorrow, you don't know what are the demands. Tomorrow, the demands are coming. When tomorrow the demands are coming, then you say, okay, now I want to connect this one. Some of them you can use your previous edges that you bought, but some new edges you may need to buy. But then you need to pay inflation factor. Of course, you may buy everything on Monday, but then you are paying a lot. Maybe there are less demands are coming. Or you may not buy anything, but the inflation you need to pay. So essentially, this is the trade-off, and you try to minimize the total cost of this Monday plus Tuesday cost. It is actually called Monday, Tuesday. This is called Steiner. This is called stochastic optimization. This is 2-stage stochastic optimization. You can consider 3-stage. Like the third day is also coming. The days, I mean, some more demands are coming on third days, but the cost would be off. This is another problem that the people consider, and it is interesting. Euler-Wright was another problem, as I mentioned. He's very relevant to this Steiner. So here, instead of SITI, in some sense, we have just the red part that we want to go there. But at the same time, we have this kind of capacities, essentially. That you may need to, you cannot just essentially, this is the van, that this van needs to go there, and there's a capacity. And last but not least, this is the, so this was about the Euler-Wright. This another one, it is called oblivious network design. This is also gonna very fundamental things that we have it. This is another very nice result, actually. Okay, what is oblivious network? Oblivious network design is somehow has some flavor of this stochastic. In the oblivious network design, I essentially buy a set of edges in advance. Good. I decide that I will buy a set of edges in advance. Whenever a demand is coming, I just route it through my network. And you can always say that the solution that you obtain it actually is here. In the uniform version, we can, non-uniform, I'm not so sure that there exists such a result, but for uniform, we say that actually, if the uniform case, the Auerbach things, Auerbach other things, in the uniform, actually, you can buy the edges in advance. You don't know what are the demands are coming. But any demands that are coming, you just route it through your things. And you will get it essentially a solution which is log n to the 3, worse than the optimum solution.
This is the one you had, the 2-stage one. You put like information tree.
No. This is different from this. There is no inflation.
Yeah, but I'm saying if in the two-stage one, you put inflation to infinity, it's the same.
If we put the inflation to infinity, then you need to buy, yeah, you can say that, yeah, that is. But I mean, you need to see, I mean, the approximation factor may depend on lambda essentially. You cannot just put the lambda infinity there. But this is a very non-trivial result. Actually, this result, this is also another thing which is used oblivious solutions, also used universal. So this, note that this is actually even stronger than this concept of oblivious. So this kind of universal or oblivious, these are actually very interesting set of problems. This is the universal TSP. This came, one of the early one is come from the universal TSP. What is the universal TSP? So in the TSP, what is the idea? Is that, I mean, you are given some places, say, some metric, and you want to find a solution that goes through all of them essentially and come back. This is the TSP. So you are given a metric, you want to, some particular point of this metric, you want to go through them, and then you will, according to some order, such that you are minimizing the total cost of this. Now, what is the universal TSP? So universal TSP actually is the postman problem. So in the universal TSP is this one. I'm giving an ordering of all vertices of the metric or the graph. Good. All vertices, I'm giving the whole ordering of all of them. And I will say that, I say, to the postman. So you will take all these letters. You will go, just use this. I mean, this is, I will print it and give it. Say, this is the path that you need to take it. If for some of these points here, so this is my list essentially that I'm giving to you. If for some of these you don't have any delivery, just ignore it. Go to the next. So this is essentially, this is the TSP. I mean, we have it like slightly better than 1.5, the approximation for this. But this is very universal. It's called universal TSP. And the people achieved back in 1980 or others. We have some other papers that improve in this result. But this is the idea that I am giving you essentially a solution. It is a universal. All points are. But when you as a postman, you are going there, you will see any place that you have a delivery, you will go there. Otherwise, just skip those places and go to the next one. I can show that there is such a path that always gets order log n times optimum. What's that? No. There was some conjecture that maybe log n over log n is possible, and even that's not possible.
There's a log n lower bound now?
There is I believe there is a log. Yeah, we are proving something log n to the 1/6. For the graph, we are proving log n to the 1/6. I think that might have been improved slightly.
So what's the best number lower bound?
I think it's log n to the 1/6 or something like this. But there are different versions of this. So if you consider in the plane, the same problem, this TSP, it would be called a space filling curve. Because in a plane, there's not infinite number of things. Then it is something called a space filling curve that you will go through all, in principle, you will go through all points. And there is such a space filling curve that is always log n.
In TSP, are we not allowed to go through the same list twice or something?
No, you can go there. Yeah.
But the optimum solution one.
The optimum, I mean, it depends. If may need to go there.
So you just need to go through it. You need to visit all of them.
You need to visit all of them. But yeah, I mean, you want to just make sure this is like, essentially, this is some kind of a spanning tree. On top of that, you will put it half matching, such that you will make the whole graph Eulerian. And then in the Eulerian graph, you are going there. That's essentially the 1.5 approximation. You need to find MST, which is a lower bound for the problem. You will get it, and then you use a matching between degree, the vertices who have odd degree. And then you will say that is at least half of the thing. So it is half plus opt. You will half of plus opt will be 3 half opt. Then you can slightly improve it, as we know this, like recently has been done. But here in this universal TSP, these are quite non-trivial actually get a solution for that, because you need to say for any set of demands that you are giving to me, I am competitive with that. So these are in some sense the hardest set of approximation. The same thing also, this universal thing also used with the term oblivious. Oblivious network design is this thing. I'm giving, like, for example, for a Steiner tree or a Steiner forest, or like in general, uniform Buy-at-Bulk. I'm giving you some, for any pairs, this is the thing. For any pairs, I'm giving some path that you will use it. Good. Now, any set of demands that are coming, I'm just using my prescribed path. And then I can show that you are would be at most log n to the 3 times opt. Does it make sense? Like, you see, that's the main problem. That you may give some path, the other one it may give the path. But the issue that if you know that these are the paths, maybe there is another place. So I'm giving this path. For the other one, this is S1T1. This is for S2T2. And then there is, maybe if I know, if you give me S1T1, then I will use something which are, both of them are joint essentially. And that is a shorter path. Because I don't know the things in advance. But I can give you the path. These paths are given to you in advance. Then any set of demands that are coming, you just use my path that I prescribed. And I can give you this, you can get log n to the 3. I'm not so sure that has been improved or not. I think that is also another thing, that log n is possible for. I think I still should be. We don't know whether log n is possible for this problem or not. For Steiner files. You see, like a beautiful things, the ultimate things. These are much harder to design algorithm for this case, because in the approximation algorithm, you know the demand, you will optimize for this. Here, I don't know the demand. I want to give some kind of universal solution or oblivious solution that whatever the demands are coming, I can just use my prescribed. And anytime you get such a thing, it is a big, essentially, surprise. There is another thing that is oblivious routing that Harald Reiche had it also. That was interesting. But that is for the routing, it's a bit different things. But anytime that such a thing is possible, such kind of oblivious or universal, with something, generally you cannot get better than log. It's hard to get it log. But polylog is possible. It is a very big surprise. And quite non-trivial. The log n is not that bad. Anyhow, this is another set of problem that you can consider universal or oblivious solution. As I mentioned, anytime if you can get for any problem such an approximation, such a result, the people will be very surprised because it's quite non-trivial. And lots of the time you cannot get it, but sometimes you can get it. Like, for example, for a Steiner tree, Steiner forest, this Buy-at-Bulk things you can get it, or for universal TSP you can get it. Anyhow, there are other things that you can consider. The capacitated network design, that each of these edges have some capacity. So it's not completely, so essentially it's not completely concave. So far we have considered concave case, that the cost of each edge is concave, but it might be the case that there is some capacity. So after some time you cannot route anything more. You need to just route it through this other thing. That's another interesting thing that you can think about. And but yeah, so this is the whole thing I wanted to give. So this is not network design, but a set of very related problems that you can think about. All of these directed, node weighted, stochastic. I mean, this kind of oblivious demands are polynomial or non-polynomial. You can think about any research problem that you have it. You can think about it, and several times this becomes non-trivial actually. And some of them, like again, like oblivious network design or universal network design, it becomes completely non-trivial, and these are hard results to get, and whenever you get it, it's like very big surprise. Good. So I think we are done here. Then we will talk about some other things about cut problems and others next time, that we can still use this kind of FRT or the RACE for that. And then we will go after that for some special graph, like more specialized problem, like facility location, or like some kind of rounding, group Steiner tree, etc., some kind of local search, and some planar graph, special graphs, etc. So that's the thing that we are talking about the rest of the graph. But I think for now, stop.